Well, good morning to those of you who are distance learning today. Today happens to be the fall equinox. All places on Earth get exactly 12 hours of daylight and 12 hours of nighttime tonight. Plus the sun, for all places on Earth, sets due east or rises due east and sets due west today. Only 2 times a year that it does that. Plus the sun is directly over the equator at noon today. That is the definition of the equinox. Today, our objective is projectiles launched horizontally, and this might not initially seem to relate to your last topic, which dealt with finding vectors in 2 dimensions, but we're going to see that it's actually going to bear a very close resemblance to that. So if you could, sharpen up your pencil, get ready to burn. We are going to learn about projectiles launched horizontally. We're going to limit ourselves only to this to begin with. It's going to be a little bit easier stepping stone into the more complicated idea of launching projectiles at an angle. So, the one thing to understand if I launch a projectile horizontally is that my x and my y velocities are going to be independent of one another. They bear no relationship to each other. One will have no impact on the other, as we're going to see. And we will, sorry about the little glitch there. So our velocities in the x direction we are going to presume to be constant. Again, for all this, we're living in the magical world where there is no air resistance. So our velocities in the x will be constant. There will be no acceleration, either positive in the forward direction or deceleration due to drag. But just as we illustrated last chapter, our acceleration in y will always be a negative 9.8 meters per second squared on Earth. That's what we are going to presume. And our initial y velocity, our velocity y initial, is going to be 0. Okay? Sorry about the exclamation points. Horizontal velocity gets me excited. Okay? So, if I were to launch an object here, let me get some of this out of here. This debris just kind of illustrate that. So if I launch a projectile from this cannonball, cannon I should say, launch a cannonball from this cannon, notice that, let's say this cannon was a dud and the cannonball just dropped straight down. We would notice that each successive second this ball would have a greater displacement. Okay? In the instance of the cannonball being launched horizontally, notice its y displacement does not change based upon that. Okay? If we were to look at these two from, let's say, a 90-degree angle from this, looking edge on straight at the cannonball, we'd see these two balls fall in sequence with one another. But this shot right here, the one shot horizontally, does have a horizontal component as well. But that is going to be constant. Notice that the distance in between each of these still shots is going to be the same amount of displacement. So this would illustrate a consistent x component of velocity, but the path of this cannonball is going to be parabolic due to the nature of the fact that its y component is going to continue to increase in magnitude. Okay? So we're going to see that. If we were to draw this with vectors, this is what we would see. Okay? My x component of velocity is not going to change. Okay, that's going to be a constant. But my y component of velocity continues to increase over time. So let's watch this fellow right here. He's going to drop an object here. Let's see if he's got a video. Whoops. Doesn't quite have the video. But if he were to just have these two and shoot one off the side, this one and this one would hit the mat at exactly the same time. So how would graphs of this motion look? Okay, let's get me out of here. Move me up to here. And my x component of velocity over time is going to be pretty straightforward. Okay, my x component of velocity over time is a consistent velocity, my displacement. So my graph of that would look something like this. Whereas my y displacement is going to, let's say we've got this as being 0 here. And my y component of velocity would look something like, whoa, that's not what I want. Looks something like so. Okay, so you can see that that is going to be drastically different. My velocity in the x direction, as we indicated, that is going to be a constant, whereas my velocity in the y direction is going to have a consistent slope that's going to be a negative 9.8. Let me just write that as 0. My slope here would be a negative 9.8 of this meters per second squared. And our acceleration for this one would be 0 the whole time. I'm not accelerating in the x direction. My acceleration in the y would be a constant negative 9.8. Now, if I wanted to know my velocity at any given point, the combined resultant velocity, all I would do is take what is my velocity in x at any given point. Okay, that's going to be constant throughout its entire path in the air, whereas my velocity in y is going to be based upon how much it's been accelerating. But if I wanted to find this total v, my resultant v, I have to do the Pythagorean theorem. What is my velocity in the x direction? What is my velocity in the y direction? A squared, b squared equals c squared. If I wanted to find the angle at which this projectile is going at any given point, I'm going to need a little bit of trigonometry. Okay, I could take the inverse tangent, take the opposite over my adjacent, and that would help give me my angle. And that's going to be part of it, because vectors are going to incorporate not just my magnitude, but also the direction. Okay. Now, to make sure we have enough time to cover this, I'm going to stop this screencast and throw another screencast at you to make sure that we can work through it methodically enough so that you get it. Okay, so that is the end of take 1. Take 2 is listed with it.